This is OwlUp, where learning happens in minutes, not hours. For a deeper journey, explore all our courses at owlup.co. Now, let's dive in. Chapter 2 of Curious Math, Numbers That Change the World, Unraveling Pi, the Infinite Quest for Precision. In this chapter, you'll learn: describe the historical development and approximations of pi. Let's dive in! A single number secretly links your coffee mug, the moon's orbit, and the code running on Google servers. Right now, somewhere, a supercomputer is spending months chasing just one more of its endless digits. Yet engineers rarely need more than a short handful of them. Walk into a hospital MRI room, a music studio, and a rocket lab, and you'll find the same silent partner in the background: the geometry of circles. Wherever waves, rotations, or orbits appear, this quiet geometry shows up in the equations, and pi rides along with it. Those digits don't just live on paper. They sneak into how we compress music files, sharpen medical images, and predict how a satellite will swing around Earth. Every time a signal is filtered, a lens is polished, or a turbine blade is shaped, someone has trusted a calculation that, somewhere deep inside, leans on pi. Artists even feel its pull, from circular concert halls tuned for perfect acoustics to modern sculptures based on spirals and arcs. As our tools get more precise, from 3D printers to quantum sensors, the question shifts: not what is pi, but how absurdly precise do we really need it to be? So why did people start stretching pi beyond the handful of digits that guide rockets and medical scanners? Partly because new questions kept raising the bar. Ancient surveyors only needed enough accuracy to lay out fields and canals. Later, navigators steering across oceans demanded tighter numbers for long-distance routes. As calculus emerged, pi slipped into formulas for areas, volumes, and wave behavior, turning up in places that seemed to have nothing circular in sight. By the time digital computers arrived, chasing more digits became both a stress test for hardware and a proving ground for clever algorithms. To see how far this quest has come, it helps to rewind to a world with no calculators, no algebra, and not even a clear notion of infinity. Early mathematicians didn't talk about irrational numbers. They had rope, straight edges, and courage. Archimedes, around 250 BCE, pulled off a move that still feels modern. He trapped a circle between a 96-sided polygon inside it and another outside it. By carefully comparing their perimeters, he squeezed pi into a narrow range. No fancy symbols, just pure geometric grit. His method planted a powerful idea: you can corner an unreachable number by boxing it in with things you can compute. Centuries later, a different toolkit appeared: infinite series. Instead of drawing many-sided polygons, mathematicians like Madhava in India, and later Newton and others in Europe, expressed pi as an endless sum of fractions. Add more terms, get more accuracy. These formulas were slow by today's standards, but they made pi a playground for early calculus and pushed people to think rigorously about infinite processes. The real shock came when pi escaped geometry altogether. Probability theory revealed that if you throw random points at a square with a quarter circle inside, the proportion landing in the curved region encodes pi. Even more strangely, certain patterns in prime numbers and random walks bring pi into formulas where no circle is drawn anywhere. This, "you thought you were done with me?" behavior is one reason modern mathematicians call pi ubiquitous. Once electronic computers arrived, pi became a proving ground for algorithms and hardware. The Gauss-Legendre approach, and later record-setting formulas like the Chudnovsky brothers' work, turned the calculation into a high-stakes competition. Each new record quietly tested memory systems, storage, and error-checking methods that later showed up in more practical software and hardware. Today, some researchers chase pi not for geometry, but to probe deep questions. Do its digits behave like perfect randomness? Can patterns in its expansion reveal new mathematics, or are we just projecting meaning onto noise? The frontier has shifted from "how many digits" to "what, if anything, are they telling us?" In practice, pi quietly steers technologies you'd never label circular. In MRI scanners, reconstruction algorithms rely on pi-laden transforms to turn raw magnetic echoes into crisp 3D slices of your brain. In streaming platforms, The math that compresses your favorite song leans on the same family of transforms, again smuggling pi into how waveforms are chopped, analyzed, and rebuilt. Statisticians see pi every time they touch the normal distribution, the bell curve governing exam scores, sensor noise, even height data in epidemiology. The constant in front of that curve isn't decorative, it's tuned so the total probability adds up to 1, and pi is what makes the bookkeeping close perfectly. In cosmology, pi creeps into models of how the early universe's tiny fluctuations grew into galaxies. Change pi, and those equations no longer match the sky we observe. In that sense, pi behaves like a universal tempo marking in a symphony score. If you nudge it, the whole performance of reality drifts out of sync. Physicists increasingly treat pi as a stress test for our models of reality, tweak it in simulations, and entire cosmoses evolve differently, like alternate endings to the same movie. In finance, pi hides in stochastic models that price complex derivatives, nudging how risk is quantified. Data scientists mine pi's digits to benchmark randomness tests, then apply the same tools to spot fraud or bias in real-world datasets, turning a circle constant into a quiet auditor of our algorithms. Your challenge this week? Pick one circular object you use daily, a pan, steering wheel, or watch face. Measure its diameter as carefully as you can, then use pi to estimate its circumference 2 ways, with 3.14 and with as many digits as your calculator shows. Compare the results and ask, where would the tiny difference actually matter? This was OwlUp, your daily step forward. To keep learning with structured courses and more insights, go to owlup.co. Until tomorrow!